glad to be here with you. Just don't call me Mr. It's very unusual to me. So Serhiy, that's much more convenient. That's how we do here in the industry, right? I'm going to tell you a class in machine learning during all these 3 days. Before we start, how many of you have heard about machine learning before? Right. How many of you did use machine learning before? Well, all right. You will be disappointed, guys, most of you. I mean, you got it fine. Okay. How many of you are data scientists, machine learning engineers, or something? Okay, that's better.
Or something.
So, this class is going to be about machine learning. And the first plan is going to be the following. Today we will just take a brief view on what machine learning is actually, and just take a few steps towards supervised learning. I know that you are already tired because it's the end of the day, so it's not going to be hard, I promise you. And you won't need your laptops at least for today, so we're not going to do any code so far. So, machine learning. First of all, take a look at those two. And they view that's very nice. But actually, they can be a disaster for you as a software engineer. Of course, they can be a disaster for you if you own them, but also if you work, say, in computer vision, and your problem is to identify who is a cat, and who is a dog, that might be a complicated problem. Imagine you have this image, just this image in form of pixel intensity. That means you have a matrix in red, green, and blue, for example, which contains numbers from 0 to 155, each of them corresponding to the how intense is each channel. And now, just having this information, you should write down an algorithm using reasonance logic to identify cat and dog on this photo as well as on many others. This, you might think, a few seconds, how would you do that if you were a software engineer? That's kind of unlike a software engineer. But in fact, this problem is somewhere between very hard and impossible to do with the conventional if-then-else logic. It's not the only kind of problem that falls in this bucket of impossible problems using standard if-then-else logic. There are many others. In addition to those, for example, among other which are impossible are, for example, speech recognition. This kind of same complexity. Apart from those problems which are impossible to do with conventional logic, we have another bucket of very hard to do problems. Those can be done with conventional logic, so you can just figure out the rules by yourself, but it's just inefficient. This kind of problem are mostly concerns, for example, with predicting something, like predicting price of your stock on stock market or something. You can eventually figure out the logic, like if something is going on in the Middle East, then the price of oil will probably go down, stuff like that. Maybe go up depending on what's going on in the Middle East. But anyhow, there are different and better approaches for solving those problems, which basically are called machine learning. There are two definitions of machine learning. First of them is given by Arthur Samuel in 1959, which also gives us the information that machine learning is quite an old field. And this first definition defines machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. The second approach comes from Tom Mitchell in 1997. It's much more complicated thing. It says that the computer is said to learn from experience E with respect to some class of tasks T, and performance measure P performance. If the performance P, as measured by the problem P, improves with the experience E. Apart from the fact that machine learning exists for more than 50 years already, we also can get the information that simple is better. That's why we will use simple approach to tell you about this class. In addition, you will have some follow-up classes like niche or something, which will be deep learning. I know that you're going to study bioinformatics in this summer school and so on. Those will be somehow based on the basics that we are going to study here. For those of you who are familiar with these basics, again, you will use them later. For those who are not, That's who you guys. So, actor Samuel himself, the guy from 1959, was famous for his checker game. Checker game was a game of checkers, which played against themselves and learned from this experience. Fun stuff is that actor Samuel, the creator of this program himself, was not a good checker player. But eventually, the program managed to learn how to play checkers better than the creator himself. So the program that he wrote was able eventually to overperform Mr. Samuel in the very same game. So what did he learn from this experience? That in fact, in 1970 or something, when the checker game was developed, the computer was able to outperform the creator of the game, of the program, right, in some specific task if it learns. Next thing that comes later was the definition of intelligence itself. It's very hard to say what's intelligence, right? Because we, as human beings, we are unable to separate intelligence from human beings. Because if you try to do that, it raises immediately the question of Chinese room. That means, for example, if a program can do something that we would require intelligence to do that, right? For example, like translating from one language to another. That was a quite clearly intelligent problem that requires human quite decades ago. Today, computer can do that, but does that mean that computers are intelligent? We don't know, because, well, maybe they just match the icons from the Chinese room. That is pretty much what they do. So when we talk about artificial intelligence today, we don't really know what it is. We cannot define what it is. I mean, what is intelligence, right? as a human intelligence without referring to human. That's why the only thing that we can be sure about intelligence itself, that it is developed by learning, mostly. We human beings, we learn from the very beginning of our life to become what we became later. And one thing we are sure, at least today the community, the research community is sure about artificial intelligence, is that it involves learning. We don't really know what it is, but we are sure that the only way to artificial intelligence is by learning. That's why machine learning today lies in the very bottom, on the very bottom of the artificial intelligence. That's another fun story because quite ago it was just one of the sub-areas of artificial intelligence. It used to be AI and then sub-areas like computer vision, machine learning, signal processing, natural language processing, stuff like that. But with the recent move of deep learning, deep machine learning itself became sort of a bottom of a base for supporting all those sub-areas. So right now we are pretty much unsure how we define AI and how we, well, make it different from ML. This took a long time, about 50 years, so let's take a look what's in there. There are three main areas of machine learning. First is called supervised learning. Remember, or maybe some of you have kids, or remember when you were a kid, how do children learn characters or numbers or whatever? In my days, we had those wooden cubes or something with the letters and some creatures, for example, which the name of the creature started from this very same letter, so we just figured out how to associate the name of the creature with this letter, and then you just take a look at some letter, say A, another letter which is the same A, and then you ask your kid, what is the letter? And she said A, like that. This is the very same thing as supervised learning suggests. You have examples with the right answers, lots of different examples with right answers, and the machine is taking a look at these examples to figure out some rules to give right answers on previously unseen examples. We have two types basically of supervised learning, right? Which is regression and prediction and classification. Sorry. They are essentially the same, and you'll see that the fundamentals are the same. The only difference is on the high level is that regression predicts some continuous variable, while classification predicts some discrete variable. That means if you would like to predict the price of your house or the price of some stock asset, bonds, whatever, the price is continuous variable, so we call it regression. For example, on the other hand, if you want to differentiate somehow distinguish cats from dogs, that's a discrete variable. It's either a cat or a dog. That's why you call it classification. That's the only difference. Everything else remains the same. So that's the most obvious examples of supervised learning, but it's not the only one. How many of you have heard about Tesla Autopilot or Google self-driving cars? Good. How many of you have heard about Bloomberg article sort of 6 months ago or so about some very cool guy, hacker, who has built the self-driving car in his garage? All right, very good. So basically, the article in Bloomberg told that, all right, now we have Google with self-driving cars with budgets of billions. We have BMW, Volvo, others with their version of self-driving cars with the budget of billions. And now we have this genius guy who has built this thing in his garage, basically. And it's like, well, so sort of cool story of a single fund who fights the corporations that do it. But the fact is that the car that the guy has built was not self-driving as we, it's the same way self-driving as the Google self-driving cars, for example, are. The car was able to steer. It was just steering. So the guy controlled the speed and stuff like that. The only thing that the computer did was just define the steering direction. And now let me show you the video from early 90s with the LV project. LV project was the first self-driving car that is known to humanity, at least using machine learning. It was equipped with web cameras, and these are web cameras of the early 90s. You probably don't want to have one on your laptop today. And what the system did is took an image from the camera and then decided which angles should be for the steering wheel at this moment in time. Let's watch the video.
Is a system of artificial neural networks that learns to steer by watching a person drive. Alvin is designed to control the NavLab 2, a modified Army Humvee equipped with sensors, computers, and actuators for autonomous navigation experiments. The initial step in configuring Alvin is training a network to steer. During training, a person drives the vehicle while Alvin watches. Once every 2 seconds, Alvin digitizes a video image of the road ahead and records the person's steering direction. This training image is reduced in resolution to 30 by 32 pixels and provided as input to Alvin's 3-layered network. Using the backpropagation learning algorithm, Alvin is trained to output the same steering direction as the human driver for that image. Initially, the network steering response is random. After about 2 minutes of training, the network learns to accurately imitate the steering reactions of the human driver. This same training procedure is repeated for other road types. After the networks have been trained, the operator pushes the run switch and Alvin begins driving. 12 times per second, Alvin digitizes an image and feeds it to its neural networks. Each network, running in parallel, produces a steering direction and a measure of its confidence in its response. The steering direction from the most confident network In this case, the network trained for the one-lane road is used to control the vehicle. Suddenly, an intersection appears ahead of the vehicle. As the vehicle approaches the intersection, the confidence of the one-lane network decreases. As it crosses the intersection and the two-lane road ahead comes into view, the confidence of the two-lane network rises. When its confidence rises, the two-lane network is selected to steer, safely guiding the vehicle into its lane on the two-lane road.
So this is just a smart way of applying supervised learning. That is the same linear regression that you might use for predicting house prices or bonds prices or stock prices, just used to predict the angle of the street view. That gives you basically a self-driving car. To conclude the story about the guy from Garage, described by Bloomberg, Jan LeCun, who has what this guy did, he did the same stuff but with convolutional neural network and running on GPU, which is just the hardware that he didn't build, and the model that he didn't invent. And the guy, his name is Jan LeCun, has actually invented convolutional neural network. He made a note in his Facebook that they think that the guy built in Garage might be pretty cool, but it is it's not innovative in any way. That's why. Another piece of information for you: you don't have to, you have to be, to take critical information about artificial intelligence that are provided by some even very respectful source of information such as Bloomberg, especially in these days of hype. So, next part of machine learning is called unsupervised learning. For using supervised learning, such as predicting stock prices or driving the car, you should give the system the data along with the correct answers. For example, the stock price requires you to give some information about the assets you have, along with the prices of those assets from the past, historical information. With Alvin, you first, as a driver, you just drive it you by yourself on the roads, right? The system records information, and then it uses the information about how you were driving to drive by itself. But the fact is that we often don't have those right answers for the data that we have. For example, think about Facebook photos of Flickr or something. We have tons of photos, tons of tweets, tons of Facebook text there. We can take it out of it, but we don't know what's in there. We don't know what this photo is about, what this text is about, and stuff like that. And this is not mentioning the smart machinery logs from internet routers and stuff like that, which produce huge amount of data, and we don't know what's in there. There is a fun statistic that today everything we have on Earth produces that much unlabeled data, which includes photos on Twitters and stuff like that. That even if we all of us would spend 8 hours per day, normal working day, on labeling this data, those things would produce more data than we can basically label. So we lose this game anyway. That's why we have another type of algorithms which is called unsupervised learning. Unsupervised learning manages to learn from data which without right answers. That's what it does. When supervised learning is mostly two types of well-defined problems, such as regression and classification, with a bunch of algorithms to solve one of them. Unsupervised learning is largely a number of separate, unrelated problems. Each of those problems has some solution that fits this problem, but they are not related somehow between each other, like supervised learning. For example, first type of problem is clustering. Clustering is combining together similar things. And the most one of the most interesting types of clustering that has been done by humanity is a tree of life. That's all kinds of living organisms combined together by some similarity. You see that archaea, eukaryotes, bacteria, stuff like that. If some of you are biologists, you might have heard more about that because I'm not a biologist at all. What tree of life suggests is that some of them are similar, so we should group them together. This is a huge group, these are smaller groups, and so on. And with machine learning, with unsupervised learning, we can do that automatically. We can take some data, some data points, some entities, and group together similar ones. Build something like this tree of life, but with your own data. For example, you might be wondering if you run a company, to which groups belong your customers. I mean, not biological groups, of course, but just what's similar between them. Because you might dedicate your marketing activities to fit them better, stuff like that. If you build your data center, you might be wondering which physical servers, work together often, because that would help you to design your data centers. In data centers you have those racks and servers in them. You have one switch per rack, and those physical servers that are in the rack communicate between each other through the switch, a single switch. But if the servers are in different racks, they communicate through another, some separate switch. So the package should go through this rack switch, and go to some routing switch, and go to another rack, and stuff like that. So if those two servers are in different racks and communicate often, you normally want them to be in the same rack, but to not overload your server infrastructure. Again, in order to do that, you have somehow grouped together those servers and applications, virtual machines, whatever, that communicate often with each other. That's another application. You also use clustering, for example, for doing space research, for investigating black matter, dark energy, stuff like that. You have lots of data from the telescopes and other research projects, and clustering, grouping them together helps understand what's in there. That's just a single problem of unsupervised learning. The next one is completely different. It's unrelated to the previous one. It's just another problem. Another problem is called anomaly detection. For example, imagine you work in Lockheed Martin, Boeing, SpaceX, whatever. You produce engines, space engines. And you need to somehow understand which of them are good and which are not. You measure, each of them goes to testing lab, you measure some features, some parameters of that engine, and now given those, you need to tell if this engine is fine and you can install it in your rocket, or it's, you should just investigate it once again, maybe something wrong with the engine. The standard approach, when we study supervised learning, the first approach that comes to our mind might be, okay, now we can use supervised learning. We know how to differentiate cats from dogs, then we can differentiate good engines from bad engines. The bad news here is that for engines, you normally don't have that many bad engines as much as the dogs or cats on the web. So you don't have that much data, and the algorithm would fail. So supervised learning would fail in this problem. That's why you need anomaly detection. Anomaly detection says you that these points just look dissimilar. Algorithm says you, hey, I don't know what's wrong with this point. It just looks strange. It doesn't look much like the points I've seen before. It doesn't fit in sort of general. It doesn't look like the majority of the points before. And you might have been fallen into this anomaly detection bugs when you travel, for example. That's the case when you go to Egypt, to Europe, to the United States, whatever. Try to use your one credit card and it gets blocked for some reason, or the transaction gets delayed and went to human processing. Why is there? It's because anomaly detection of your bank algorithm finds that this transaction doesn't look much like your previous transactions. This transaction is suspicious. For example, if all of your transactions before have been made in Lviv, Ukraine, and now you have the first transaction from Egypt, that might be a fraud, probably. That might be your vacation, but also might be a fraud. That's why they would send this transaction to a human officer to monitor it. That's good news for you because that protects your bank account from fraud. but this also might prevent you from having a good vacation if you get stuck with it in some restaurant, for example. So these things work, but these things have drawbacks, and you meet them every day, usually. Next is the cocktail party problem. That's the toy problem. I mean, it's not real. It's just a name for a group of problems. The cocktail party problem is like the following. Imagine you are on the cocktail party. You know, by the way, what's the difference between cocktail party and standard party? Who knows the difference? Right. I'll tell you. On a standard party, you do dancing, listening to music and stuff like that, just enjoying life. On cocktail party, you take a cocktail and you go and talk to people. So cocktail party is like business kind of party, you know? They do have music normally, but in the background. So they don't normally crash you and with some buzzes or stuff like that. So cocktail party is for communication. The problem is called after this cocktail party because imagine you are on this kind of event, you talk to a person, you have a conversation. At the same time, lots of people around you also have a conversation, and you hear your partner as well as those who talk around you. The algorithms for solving cocktail party problems suggest the way to separate the voice of your peer from all the noise around. So basically, if you just record you record everything that's going on around you, and then the algorithm can manages to separate the voice that comes from your conversation from all other. Of course, no one would use this stuff to separate conversation on a cocktail party. For example, think about brain-to-computer interfaces. They look like a giant spider that you put in your head, and this stuff has electromagnetic sensors that measure the intensity of electromagnetic field in different parts of your skull. This gives you some information. For example, emotive epoch, this kind of sensor gives you 14 channels. It puts 14 sensors in your head and just record 14. 14 intensity of electromagnetic field from 14 points in your skull, 20 or something times per second. But we can use it, of course, for predicting some stuff that you're thinking about. For example, if you want to predict what letter would you like to print, then we might replace the keyboard with this kind of brain-computer interface so that you can print without touching the keyboard, stuff like that. But what's the problem is that we don't really know what is the brain. I mean, we human beings don't really know what's in there. I mean, we know physically what's in there, but we don't know how it works. And when we measure intensity of electromagnetic field in some point, we don't know what this signal comes from. It might come from some several parts of the brain that are responsible for something, just combining. Same thing as with cocktail party. And these algorithms help us separate signals that go from different parts of the brain in the same sensor, and then we can use this separated signal for doing some analysis. One of my students here in the IT school have done, a group of students, basically, have done a class project in brain-to-computer interfaces. There is a problem, I mean, this input of characters from your brain are very, how do I say it, imprecise. So it often fails. It often fails to understand what letter you're thinking about, and you eventually went mad. No matter how calm you are, you went mad eventually because it's really imprecise. So somehow you think, oh my god, it's crazy, it's a stupid thing. And now the problem was, the idea was, if you can capture from this brain-to-computer interface your thought about that, I hate this stuff, it's crazy, then you can understand that the previous character was probably wrong and you should replace it with something else. So, the dataset was in Kaggle, and they used it for building their project. They used simple supervised learning, nothing that special, to build a classifier. If you're mad or you're not mad, that's simple. But well, standard accuracy was like 60-something%, I would say, with zero data. Then they used algorithms for solving cocktail party problems to separate these signals that go to this brain-to-computer interface. And that increased their accuracy up to 10%. I don't remember the digits at the moment, but that's what it said. The final accuracy was 70+% on understanding if you are unhappy with the previous character based on purely on the electromagnetic signals from your brain, which was pretty good. You can also find lots of application of cocktail party problem in signal processing, with all those, well, getting the signals, processing signals, stuff like that. All signals, I mean, not only communication signals, but also from some space entities, studying some marine life, stuff like that. Lots of application there. Next fun application of unsupervised learning is 3D reconstruction. There used to be a way to reconstruct 3D image from the single 3D from a single image, but it required a lot of manual input. You would be required to say that these things are the same planes and these things are the same planes and stuff like that. The guy from Stanford, his name is Saxena. He's known by his second name, Saxena. He's pretty famous today in the scientific community. He was wondering if we can do that without the human input, if we can somehow understand things about those planes without human intervention. He used clustering, the very same thing that groups together form of life, so your customers, to group together some areas, some pixels on the image. And that helped him to build a system that captures the scene from a single image. This is the gate of Stanford University, and that's how it works. You can also find the papers and even some code following those links that I provided in these slides. That's the unsupervised learning. So now we know supervised and unsupervised learning, which normally is all that classes say, like on Coursera would give you. But there is a third type of machine learning, which is called reinforcement learning. If supervised and unsupervised learning, they were mostly about making sense out of data, right? Supervised learning is predicting something, unsupervised learning is grouping something, finding anomalies, stuff like that. Reinforcement learning is different. Reinforcement learning is about controlling stuff. It just solves the problem of control. And it solves the problem of control by trial and errors. This is trial and error. This is basically the error, right? It works very much like your pets. How many of you have pets? Cats or dogs, maybe? Oh, good. Then you should remember that when they were small, well, just imagine you in the shoes of those pets. You've been taken out of home from your mother and put in some completely different environment. And then you should somehow manage to live in this environment in your house, right? Because for you it's your house, and for this small creature it's just unknown environment. And this small guy tries to do things this and that, and you just tell it good puppy or bad puppy depending on how it goes, right? And over the time, this small buddy learns how to be a good guy and how not to be a bad guy. So the thing that you give this puppy or kitten is called reinforcement, basically. Reinforcement might go in a way of food, that's a good reinforcement, you know all that, or in a form of punishment when this small guy does something wrong. That's the very same thing that was reinforcement learning. But instead of your puppy, you have your algorithm that does things, try different things, and you just provide it with the reinforcement. Like, you just tell this algorithm how good it does, basically. If it does very good, not very good, and so on. And over time, the algorithm managed to learn how to do good things, how to get the highest possible reinforcement. There's a fun story about reinforcement learning. How many of you have heard the name of Andrew Ng? He was a professor at Stanford. Very good. Before he was a professor, normally a person goes to graduate school, so he used to be a PhD student someday. And during his graduate school day, he told a story. He went to every person he could find at Berkeley when he was a PhD student and asked this person, what's the hardest engineering problem you know? So that's That's his approach for being a PhD student, right? And most of them told him that flying a robotic helicopter, that's the hardest engineering problem that you can find. That was early 2000 something, 2003, 4, 5, I don't know. And those days, flying a robotic helicopter was really hard. We just didn't know how to do that. Because imagine if you are a human pilot and you are sitting in the cockpit of the helicopter. You have 2 controls for your hands and 2 controls for your legs, and you move. The pilot moves it's all the time to keep helicopter balance. Then Andrew told that his thought was the following: okay, I know math very good. I will write down a very complicated mathematical model that would describe a helicopter, and I can use it for flying. He didn't complete this project, but he had a friend who did that. So this is the recording from the friend of Andrew Yang, who has done this very complicated mathematical model that flies a robotic helicopter. And when this video plays, you will hear the word enable control. In this moment, the control is passed to the computer.
Enable control!
So that's the result of 5+ years of research made by a professor and a group of graduate students to fly a robotic helicopter. At this point, it became quite clear that writing down some complicated mathematical models was not the way to fly a robotic helicopter, right? Maybe you can do that if you spend infinite number of hours of your grad students, which is cheap but not that cheap, and there might be a better way. Then Andrew switched to a different approach. He said, okay, I understand, that won't work. Then I will use machine learning to do that. I will use that reinforcement learning, which is trial and errors, right, to fly the robotic helicopter. They have written a simulator of the helicopter, because when you do trial and errors with a physical helicopter, that would be not much cheaper than spending infinite number of grad student hours. So they wrote a simulator of the helicopter, and they tried to fly a model of the helicopter in the simulator. Then they've taken this model that was trained on the simulator, they put it into the real helicopter, and that's what they got. That's the world's very first robotic helicopter. For example, not only fly autonomously, it was able to move airbags. Now it flies completely under control of the reinforcement learning. Again, this helicopter might look small, but in fact it's huge. It's 1 meter plus something. It's gasoline and fuel and stuff like that. We know to do that stuff. So on this recording it looks small, but in fact there was cases. These things happened on the baseball, some stadium on Stanford campus, and the people who drove near this Stanford called 911 and say that something happened on Stanford. The helicopter is going crazy, and you might want to go over it. So that was the world's very first robotic helicopter that was built with this reinforcement learning. And during that time, the research was pretty active in this area. For example, that's a news from ETH Zurich from Switzerland. Their research was dedicated to pole balancing and pole aerobatics with drones. this thing was driven by the reinforcement learning. Next, there are robots that we can build only with reinforcement learning.
We just come across down this way. Good, right through the middle.
Interesting is that it moves pretty much like the real snake, but the robot has figured out by himself that that's the best way to move, having this control that it has. So the snake does a good job probably with moving. Next, how many of you have heard about DeepMind company, Google DeepMind? Right. They've done that. AlphaGo was playing Go recently. But they started with playing Atari games. DeepMind was acquired by Google for $500 million in 2013, I think. They didn't have a single dollar in revenue, and all they had is the algorithm that played Atari games from 80s. That was pretty much unusual for the business world. But what was unique in this thing is that when you fly a helicopter, you provide the algorithm with some measurement. For helicopter, it's some angles and positions, stuff like that. DeepMind used reinforcement learning for playing Atari games, given only the screen as an input. So they didn't give. The algorithm doesn't have any information about that, the dynamic of the game. The algorithm doesn't know anything about what's in there. It only has the screen, and it was enough to play Atari game at the level of often at the level of human player, basically. Next, with the AlphaGo, they also used reinforcement learning, but it was a heavy combination of different approaches. So AlphaGo is not like distilled reinforcement learning, while the Atari game is. I'll show you, well, in SoftServe, a while ago, I've been director of data science at SoftServe, and my group there has replicated the paper of DeepMind and put it open source. It was one of the, 3 or 4 at those times, open source implementation of DeepMind technology, and that's the recording not of DeepMind, but of SoftServe implementation of DeepMind. So that was done by our guys. This is the game. We know it as Arkanoid, and Atari has their own name for it. The system learns to play it using just a screen as an input. So all it has is just the pixel intensity of those squares, that's it. It doesn't know anything about the dynamics of the game or something. It works just like that. And the results are pretty good. It manages to move this bottom thing quite right, for playing with this ball or whatever it is, to manage to break down those bricks. So that's the 3 parallel paths of machine learning that we are going to investigate during this small class of this summer school. And before we go forward, maybe someone have any question? Yes?
Did the system know where the result is standing on this image? Like, did it have to figure out the result as well, or was that given?
It gets just reinforcement as a reward. And the reward is, what was that? If it breaks the brick, the reward is 1, and if it fails, the reward is -1. The rest of the time, the reward is 0. So it doesn't know what's happening, it just knows when it fails or when it does something good. So that was the theme. Alright, let's go further. Now we start with supervised learning, and now the fun, it's going to be a bit less fun than the deep battery, but supervised learning. Imagine you would like to predict housing prices here in the city of Lviv, right? You collect the information, which is simple. You just go to a website with announcements and get the information out there. This can be done in 30 seconds. The information would look like this. You have some specification of your house, like the space, its apartment, somehow, and the price, rating price in the local currency. Now you have some sort of data, and now what you can do with this action? Well, you can draw it, you can plot it, and if you plot this data, it would look like the following. Well, what can we see from this trend? We see that the price starts from some bottom level, right? It doesn't start from zero, which is logical, and then it grows with some trend, some linear trend or something. Now, we would like to use some model to describe this price. Well, as we can see, if it is as it is a line, right? Then we can use some line to describe these prices. We can use some line like this. We would say that the price is some base price, which is the bottom level, plus space multiplied by some coefficient. The coefficient, well, we would say just how 1 meter of increase in space would contribute to the growth in price. That's how it is. Well, you might also say that space itself might not be a very good indicator of housing price, because lots of other things contribute to the price. If it's, well, how old is the building, what's the neighborhood, how many rooms, bedrooms, and stuff like that. So maybe you would like to extend this description somehow. For example, the next idea that might be a good one is to maybe add number of rooms that you have for each of your houses. Now, the model might look the following. You still have some base price plus some space multiplied by the coefficient theta 1, and plus some number of rooms multiplied by the coefficient theta 2. You might say, all right, some of those features might reduce the price, but that's fine because the coefficients might be negative, and this way you will just adjust. That's fine. So adding more features would result in additional elements of those polynomial, and you normally don't want to write it down in infinitely large. That's why we in machine learning would like to decrease it to some different representation. We call this model that describes the thing that you would like to predict. We call it hypothesis. There is no good reason why we call it hypothesis. It's historically. So we call it H fact. That's hypothesis. That's all you need to know about it. Next, we call this base thing theta 0, or a bias term. Everything needs a bias term. Everything is biased in the world around, and we know that already from our previous experience. So why not our model to be biased? I mean, it's not because of those coefficients are bad. It's just because we need some coefficient that will be multiplied with just one, to increase the accuracy of our model. Next, again, that's better than this one, right? Because it's shorter. But that's the only improvement. We still need to write infinitely large polynomial to describe I mean, not infinitely, but pretty long polynomial to describe some pretty big model. So now we would like to move to a vector representation. As you know, we can write down everything as a vector. Sorry, we can write down everything as a vector. So this sum might be reduced to theta transpose x representation, when theta is a vector of those coefficients and x is the vector of those features. We call them features. Each of these things that describe the entity of your interest is called feature. For the house, we have two features. Space is feature number 1, or feature number x1, right? And number of rooms is feature number 2, x2. We also add to this feature vector 1 at the beginning. So we have also x0, which should be multiplied here, but x0 is always 1. So we can just, well, you can see it here, but we can just reduce it out. Next, now we have a model that tell us the price of the room, of the house. That's the good news. Next, now what we would like to do with it? We would like to identify those coefficients which would give us the best results, the best prediction. And the next question that comes that comes to us is, how do we measure the prediction? How good is the prediction? Well, if you didn't know this, take a look at this. That's the good example of predictions that are not very good, and that's basically the situation we would like to avoid. That's why we need some measurement of the prediction. This guy basically thought that this lady would have 4 dozen husbands in few months because, well, the data says that. That's not a good prediction, obviously, and we would like to avoid this situation. In order to do that, you can take a look at this later also. In order to do that, we need some function, some measurement of what a good prediction is. You can pick any one. There is no reason why wouldn't you pick something that you like. And there is no reason why wouldn't you pick this one that I will show you in a moment. I'll show you tomorrow maybe, maybe the day after tomorrow, that how you can use your own cost function and build your own models using your own special cost function. But for the time being, let's pick this one. This is known as d-square function, and it says how bad is your prediction. We also, in machine learning, we call it cost function. The higher is the cost, well, the worse is the prediction. What we would like to do, we would like to minimize the cost function. So our objective is to find those coefficients of this function. Do you remember that hypothesis function depends on x, but also have those coefficient data that we might adjust. So we would like to adjust those coefficients in a way that reduces this cost function, to make this prediction as less bad as possible. So far, are there any questions about this? All right, good. Next, how would we do that? The derivative helps. One of the most powerful methods of optimization basically relies on the concept of derivative. Back in high school when we studied derivative, I wasn't sure why we do that, because a line that is tangent to a function, so what's the use of it? But later, when it comes to machine learning, I realized that wow, that's amazing. That's amazing part. So why would we use the derivative? Do you remember the derivative is basically a tangent line that is tangent to some function? What's the use of it for us? Well, the angle, right? The line, the derivative is positive when it is when this angle is less than 90, right? And it's negative if this angle is more than 90. So that's okay. That's fine. What's with it? Well, if it is positive, then the minimum of this function is backward, right? You should do a step backward to go to the minimum. And when it is negative, then the minimum of this function is in front of you. So you should somehow move forward in order to get to the minimum. That's the information that we use. So we just identify those coefficients data randomly, and then we take a step depending on what's the sign of the derivative. The derivative of the multivariate function, I would say, is called the gradient. Gradient is partial derivative. So you just take the derivative of theta 0, say, right? So that's just the derivative of theta 0 gradient, right, with respect to theta 0. And then you make a step backward if it's positive, or a step forward if it's negative. In other words, you make a step in the direction opposite to the sign of this gradient. Then you do the same with theta 1, theta 2, and stuff like that. So that's the only thing that you use. And that's the thing that used to train machine learning models during the last, well, 50 years and actively 30 years. Backpropagation algorithm, which is the thing used today to train our deep learning neural networks, stuff like that, is the same thing. It's same gradient descent. Speaking about gradient descent is an algorithm for training models using this concept of derivatives. The gradient descent rule is the following. It says update value of data, each of them, with the following. Those two dots are wrong, just ignore them. So update with the following. Take the previous value of those data and subtract from it the value of the gradient times some coefficient alpha. Alpha is known as the learning rate, and it is used to ensure convergence, to make sure that the steps are small enough and it doesn't diverge. It doesn't go, it doesn't just jump on those functions. The gradient itself has a nice property that it reduces when it comes to the bottom, to this minimal function. So this element would be smaller and smaller as the algorithm approaches the bottom of the function, the minimum that you would like to see. But this rule is only for one training example, and now we have different approaches. How would we generalize it to numerous training examples? In our data set, we have a large number of training examples, right? If it is a big data, it's even larger. And how would we train on large number of data? There are three ways, basically, of doing this. This is how gradient descent would look if we describe the gradient. So we just take the gradient. This is the gradient. Now we put this gradient here, and that's a new rule for the gradient descent that has all known variables, right? We know that cost function at the moment is least square, so that's the gradient of the least square, and that's the update rule of those coefficients theta using the least square cost function. Oops. Now that's again for a single point. If you come many points. There are three ways of doing this. First is called full batch gradient descent. Our function that I mentioned before is not actually a function as an analytical function. It is described by the number of your points that you have. Because again, remember the cost function was it was the difference of your prediction and the tag on all of your points squared, right? So basically, how bad is your model? It is described by each and every of your points. So the one thing you could do, you can take all your points, calculate the derivative, the gradient on all of them, and then use this calculated gradient to do a single step. What's the advantage and what's the disadvantage of those approaches? The gradient, the descent basically would look like this in this way. So that's the top view on your function, right? That's some minimum, and that's how you start with some initial initialization of the function. And then you take the gradient and you do the first step, and you are here. Now the second step, the third, and so forth. You know the gradient exactly. You've calculated it precisely. It corresponds. It is accurate. It's perfectly accurate. It describes your exact function. So each of your steps will be towards exactly minimum. Each of your steps will be towards minimum. That's the good news. The bad news is that you have to look at all your data points to calculate that precise derivative. And if you have lots of points, that might be computationally complex. It just takes too much time. Moreover, if you have a big data, and you know the definition of big data is the data that doesn't fit your memory. It's just too much. You're unable to calculate the gradient on all of your points because you can't put all your points in your memory. Of course, there are hacks and stuff like that, but that's not how you would approach this. So that's the good news and the bad news about the full batch gradient descent. Alternative approach is known as stochastic gradient descent. With stochastic gradient descent, you use only one single point to do a step. The next step you do with the next point, and so forth. With this stochastic gradient descent, the descent would look like this purple line. Compare it with the red line, which is full batch gradient descent. The purple line is the stochastic. Why it's that bad? Well, because it's every point adds some information to your model as well as some noise. Because some of the points might be outliers. For example, you might want to fit this kind of data. And by accident, you might, well, you just get this kind of line, which is good after some steps of training. But eventually, you will end up examining this point. And when you calculate gradient on this point, using this stochastic gradient descent, it says that the error is large, and you should put your line here. So this step would increase accuracy with respect to this point, but will reduce accuracy with respect to the whole model on whole points. That's why you will have those steps in the direction almost opposite to from the minimum. So that's the stochastic gradient descent. If it's that bad, why on earth would you need it? It's useful when you have continuous flow of data. Imagine you're Google and you're showing ads to your users. You go to Google, you search for something, and Google decides if it wants to show you an ad and what exactly ad should be shown. So it shows you an ad, and you either click or not click, or you don't click this ad. So the Google gives, it gets the information about your action immediately, and it can update this model in a continuous manner. Users serve, Google gets the information and updates the rules. This way, it doesn't have to retrain the model. If the pattern changes somehow, then the model changes at the same time. Because with the time, of course, the behavior of users changes and stuff like that. Something affects the housing prices. Stochastic gradient descent eliminates this problem. It can be, well, it's the process of endless training. It trains continuously. So you can put it into production with this stochastic update rule that is on, and it will adjust automatically to any changes in trends and behavior. There is a survey of training our models, which is called mini batch gradient descent. It combines the best out of two worlds. The intuition is like the following. Okay, we know that full batch is computationally expensive, and we also know that stochastic is pretty much imprecise because of the direction of the gradient, right? If the gradient is calculated wrong, like with this point, then we'll have step in the opposite direction from the minimum. So we just need this. This is good because it's fast. You can do one step with one point. You don't waste your time calculating the gradient from all the points. But the gradient might be imprecise. So what if we take some subset of your points out of your training set, right, and calculate the gradient not with one point, but at the same time not with all of them, but with some random subset. That wouldn't give you the best possible gradient because the subset of the points is still a subset. It describes somehow imprecise, I would say, the function itself, but it's much better compared to the gradient based on a single point, and it's still much faster than the whole number of points. This is called, again, mini batch gradient descent, and it's today sort of a standard approach with training machine learning models, whatever is the problem. No matter if you have lots of data, few data, if you have deep learning neural networks, or you have linear regression, you would normally use mini batch gradient descent because it's just that efficient. It's amazingly efficient. And again, mini batch gradient descent is another one, along with the stochastic gradient descent, training algorithm that works with big data. With big data, you just take a random subset of your points, you calculate the gradient, and you can take a step of update rule using this gradient. It also fits the MapReduce. I know MapReduce is obsolete, but it wasn't there at least a year ago or something. It fits, the paradigm of the functional programming. Think about it the following way. You can take all those examples, right? You can break them down into some even smaller subsets and assign each of them to different workers, meaning different machines. Each of the machines would calculate their own gradient, right? They have different subset of points, so the gradients will be different. But then your reducer take all these gradients and just average them. And this will be the same average as the gradient for this mini batch gradient descent. The paper of this approach was published in 2010, I think, So it's pretty recent thing. The good news is that mini-batch also can be parallelized on Spark, on GPU, or whatever you like. So that's the summary of our introductory meeting on machine learning. You can, in order to define machine learning problem, machine learning model, you need first the hypothesis. You need a model that would describe something you would like to predict. We used a line, a linear regression, that's fine. Next, what you need is some cost function to understand how good, how bad is your prediction. Then you can compute the gradient of your cost function and use gradient descent to train the model. Which kind of gradient descent to use? Well, if you have quite a small number of data points, you can use a full batch. This will be precise, but computationally expensive. If you have continuous flow of data, like if you're Google, you can use stochastic. This will, well, be imprecise, but it gives you, continuous process of change. So you can put it on production and you don't have to update the model, it will update itself. And if you use big data, if you use deep learning and stuff like that, you would probably like mini-batch gradient descent. You would probably like mini-batch gradient descent if you play with machine learning at home as well, because that's so efficient and doesn't require expensive hardware. You can train a model pretty fast on your own laptops or desktop computers. So that's all for today. Any questions? Yes?
Should we absolutely, when using the first way of updating the weights, when you use all
batch.
All the examples at the same time, should we use the sum or the mean of the errors of the neurons? Because if we just increase the quantity of the same neurons, the same examples, we will have this sum bigger and bigger and bigger every time.
It doesn't really matter. You can put the mean here, but you can have this alpha. So basically, mean can be incorporated into this alpha. Well, normally we use mean, of course. Any more questions? If not, then thank you and see you all tomorrow.